Game Theory Class 4 Video 3. In this video we're going to do some examples calculating Nash equilibrium. Let's begin. So let's look at this example here. If you remember, this example is called the prisoner's dilemma. Okay, and the context behind it is L stands for loyal, B stands for betray, and the numbers tell you how many years in jail they get. But that's not really important when it comes to calculating Nash equilibrium. So let's calculate the Nash equilibrium. If you recall, a Nash equilibrium is an outcome where neither party can unilaterally improve their payoff by changing strategies. So let's just examine all of the outcomes one by one and see if it's a Nash equilibrium. So the first outcome to examine is L, L. Okay, is this a Nash equilibrium? Well, if you think about it, if player 1 changes their strategy from L to B, then their payoff goes from -1 to 0, which is an improvement. That's an improvement for player 1. And similarly, if player 2 changes their strategy from L to B, then their payoff goes from -1 to 0, which is also an improvement. So in this case, neither player are content. So no, it's not a Nash equilibrium, because neither player is content staying there. Both players have an incentive to change. Let's try a different one. Let's try LB. Okay, so now if we think about it, we're considering this one here. If player 1 changes, they go from -3 to -2, which is an improvement. Okay, like, try not to let minus numbers confuse you, but -3 to -2, that is an improvement. So that means player 1 has an incentive to change, which means that this is not a Nash equilibrium. Okay, let's try BL. So I'm looking at this one down here. Okay, if player 1 changes, they go from 0 to -1, which is not an improvement. That's actually getting worse, right? Going from 0 to -1, that gets worse. So player 1 is content. Player 1 does not want to change. But if player 2 changes, they go from -3 to -2, which is an improvement. So player 2 is not content. Player 2 has an incentive to change. And in Nash equilibrium, you need both players to be content. So this is also not a Nash equilibrium. Okay, the last possible outcome is BB, betray, betray, which is this one here. So let's think about what happens. If player 1 changes from B to L, they go from -2 to -3, which is not an improvement, right? That's actually getting worse. So player 1 is content. Player 1 has no incentive to unilaterally change. What about player 2? So if player 2 changes, they go from -2 to -3. If player 2 changes from B to L, they go from -2 to -3, which again is actually getting worse. So both players in this case are content. They can't improve the payoff by changing. So BB is a Nash equilibrium, and it's the only Nash equilibrium in this game. Okay, it's interesting to note that BB is obviously not the best outcome, right? LL seems like it's a strictly better outcome. It's better for both people. In LL, both players only have 1 year in jail, whereas in BB they get 2 years in jail. But nonetheless, BB is a Nash equilibrium and LL isn't. The trouble with LL is it's a situation where both players can look at it and they can try and exploit the situation. They say, if player 1 is considering, being in LL, they think, well, if they change to B, their payoff goes from -1 to 0, which is an improvement. And player 2 actually thinks the same thing. So they both want to change. Even though LL is better for both of them, like selfish behavior would make them swap to betrayals. And then this is what I was talking about, how you end up getting stuck in a Nash equilibrium. You'll end up getting stuck in BB, which is here. So let's do another example. This example right here. Same thing, calculate the Nash equilibrium. Okay, so I'm going to go through all of the outcomes one by one and check to see if it is a Nash equilibrium. AX. So if I'm in AX, that's this one here. If player 1 changes from A to B, they go from 0 to -1, which is not an improvement. It's actually, it gets worse. So player 1 is content. Player 1 does not want to change. If player 2 changes from X to Y, they go from 0 to -1, which again gets worse. So player 2 doesn't want to change either. So that means that this is a Nash equilibrium. But just because we found one doesn't mean we can stop, because there might be more than one. So we have to check them all. If we look at AY now, that's this one right here. If player 1 changes from A to B, they go from 0 up to 9, which is a big improvement. So player 1 has an incentive to change. And I don't even need to consider player 2, because the fact that player 1 has an incentive means that it's not a Nash equilibrium. To be a Nash equilibrium, you need both players to not have an incentive to change. Let's move on to the next one, which is BX, which is this one here. If player 1 changes from B to A, they go from they go from -1 to 0, which is an improvement. So again, player 1 wants to change, which means that this is not a Nash equilibrium. Lastly, let's do BY, which is this one here. Now, if player 1 changes from B to A, they go from 9 down to 0, which is not an improvement. That's actually getting worse. So the player 1 does not have an incentive to do that. If player 2 changes from Y to X, they go from 9 down to 0, which is also not an improvement. It's actually getting worse, so they don't have an incentive to do that, which means both players are content. They don't have an incentive to change, so it is a Nash equilibrium. Okay, so in this game here, there are two Nash equilibrium. They are AX and BY. Okay, and notice how one of the Nash equilibrium is a lot better than the other one. BY is a much better Nash equilibrium. I mean, you get 9-9 as opposed to 0-0. Right? BY is the much preferable Nash equilibrium. But it's perfectly possible that if you were playing this game with someone repeatedly, you could get stuck at AX. Okay, so this is a type of game where it makes sense to try and coordinate beforehand. If you were playing this game with someone, you know, what would be really nice is if you could both agree beforehand, like, why don't we just try and get the 9-9 outcome? It's better for both of us. You know, it's mutually beneficial. We should just coordinate and try and get the 9-9 outcome. But you can't always coordinate when you're playing games. That's the end of this example, and it's the end of this video.